All right, let's finish up our work in continuity by talking about the intermediate value theorem. So one new vocabulary word here, it's intermediate value property, and then we have a big theorem. It's the intermediate value theorem for continuous functions. So let's begin with this. Functions that are continuous on intervals have properties that make them particularly useful in mathematics and its applications. One of these properties is called the intermediate value property. A function has that, the intermediate value property, if it never takes on two values without taking on all of the values in between. So for instance, if you said that f had some value f of a, say for instance that might be 100, and you also knew that it took on or had the value at some point 200, then a function with the intermediate value theorem would, in all cases, would somehow take on every single number between 100 and 200. That's the intermediate value property. So here's the formal theorem. A function y equals f of x that is continuous on a closed interval a to b takes on every value between f of a and f of b. In other words, if y naught is between f of a and f of b, then y naught is equal to f of c for some c in a, b. So here's what we mean. If you know that a function has a y value f of b and another y value f of a, then for some value between a and b, this function takes on literally every single y value between those two y value boundaries, f of b and f of a. That might seem like a very obvious statement and maybe not even enough that it needs to be singled out for special attention, but that intermediate value theorem is important because it provides a foundation for many fundamental theorems that calculus is built on. The first part of the intermediate value theorem, where we said the function f was continuous, we'll point it out here, that's the part that's so essential. If a function is discontinuous anywhere in the interval, this theorem's conclusion may not be true. It might fail. Here's an example of that function below. So we look at, say, f of 1, and we have 0, and we look at f of 4, and we have 3. So f of 4 is that, and f of 0 is that. But this function does not take on any of the values between 2 and 3 because this function has a jump discontinuity at x equals 2. So the intermediate value theorem depends on the continuity of the function f. Here's an example for us that can use the intermediate value theorem. Is there any real number that is exactly 1 less than its cube? And then compute that number accurate to 3 decimal places. So algebraically, what are we trying to do here? We're trying to find a number x such that that number is exactly 1 less than its cube. So x cubed minus 1. That's really what we're trying to do. And we could probably rework this statement into saying x cubed minus x minus 1 equals 0. So what we're really trying to do here is look for a 0 to the function f of x is x cubed minus x minus 1. Look for a 0. So we may even begin by just kind of taking a look at a few numbers and see how this function behaves. So what happens if we plug in, say, 1? We get 1 cubed minus 1 minus 1 again. So 1 minus 1 is 0, minus 1, that's a negative 1. What happens if we plug in a 2? So we would get 2 cubed minus 2 minus 1. So f of 2 is 8 minus 2, 6, 6 minus 1, 5. And here's where we can apply the mean value theorem. Since f of 2 is 5, and f of 1 is negative 1, and this function is a polynomial and it's continuous, we can now know for sure by the intermediate value theorem that this function takes on every single value between negative 1 and 5. Therefore, it must have a 0. So let's take a look at this in a graphing calculator. Let's graph y1 equals x cubed minus x minus 1 and figure out if we can find its 0. Where does it cross the x-axis? So to our graphing calculator, let's go to y equals screen. Let's try x to the third minus x minus 1. And let's go zoom decimal. And we should start to see this function being graphed. And there we are. Yes, there's a 0 between 1 and 2, just as we suspected. And we can ask our calculator to find that value exactly by hitting second F4, which is the calc menu. And we want option 2 for the 0. The left bound, let's make 1. The right bound, let's make 2. And then we're asked for a guess. How about maybe we'll guess 1.5 right in the middle. And there we have it. I'll turn this a little bit bigger. We have 1.32 and then round to the third decimal place 5. 1.325 is where this function has its 0. So 1.325. And that concludes all of our study on continuity.